So welcome to part one. In this section, we're going to address the basic pharmacology of psychedelics. Pharmacology being the study of drugs, how drugs work. And so we need to start at a very low level in scale. We're looking at molecules here, and we're looking at a particular brain chemical, a neurotransmitter, a hormone, a very simple hormone, an amine hormone. Hormones are just signaling chemicals, so they cover a lot of different chemicals in the body. And we're focusing on serotonin, and you'll likely have heard of serotonin, probably in the context of mood. You might have heard people describe it as a happy hormone. Maybe you've heard people say that it's linked to depression, and if your serotonin levels are low, maybe that explains your depression. Of course, that's massively dumbed down. It's partly true, but the reality is it's a little more complex and interesting than that. But psychedelic drugs, psychedelic being a term coined in the 1950s by a British psychiatrist, Humphrey Osmond, refers to really the key property of what these drugs do to the mind, which is to reveal the mind, its content, its depth. And that's quite hopefully an interesting theme, that it's a reminder to us that there's a lot of the mind that isn't so easily visible to conscious awareness. And so with the coining of this term, Humphrey Osmond, in collaboration with Aldous Huxley, who we'll talk about later on, wanted to kind of capture that essential property of what these drugs do, that they open the mind up, they reveal its content, its true depth. And so psychedelic, mind manifesting, mind revealing, is referring to that key property. So that's our definition of psychedelics, at least in terms of the etymology, where the word itself comes from. But we can also define these drugs based on their pharmacology, how they work in the brain, and that's where serotonin comes in, this happy hormone. And serotonin, this signaling chemical neurotransmitter, most of it is actually found outside of the brain. 90% of it is found in the so-called enteric system, or the gastrointestinal system, your gut if you want. And there it controls bowel movement and motility in the gut. It's generally associated with constriction, similarly with the vascular system, blood. What it does in the brain is, first of all, quite complex. It does a lot of different things. Serotonin is a neurotransmitter, but it's a particular kind of neurotransmitter. Neurotransmitters are signaling chemicals in the brain, transmitting signals, right? And serotonin is what we call a neuromodulator. So rather than being a neurotransmitter that works more like fuel in the system, or some kind of inhibitory chemical, so the fuel, glutamate, an inhibitory chemical, GABA, they're more like the kind of hot and cold of the brain. With serotonin, we have a modulator, which is more of a kind of subtle tuning of the brain. And serotonin is a very complex neurotransmitter, as I said, a neuromodulator. And speaking to that complexity is the fact that it has a very broad range of what we call receptors. And these are the proteins. These are proteins that sit in the membrane of important brain cells, neurons, the brain cells that do most of the important signaling and passing of electrical signals and chemicals between each other. And so these receptors sit in the membrane, and when neurotransmitters bind to them, they initiate a signal within the cell, and that signal changes the behavior of the cell. And there is a number of different ways in which you can change the behavior of a cell. So, for example, through one receptor, you might initiate a signal that makes the cell more excitable. And then another receptor might make the cell less excitable. And there's a number of different varieties on that. And so serotonin has, we think, something like 16 different receptor subtypes, speaking to that broad complexity of this system. Just to put that in a bit of context, you might have heard of another neurotransmitter, dopamine. The number of receptors identified for that is more like, I think, less than 5. So serotonin, to my knowledge, the most complex neuromodulator that we have in the brain. And we know since the 1980s that one of the 16 different receptor subtypes is critical to the action of psychedelics. We first discovered this because it was found that there's a near perfect relationship, like a straight line, between the affinity or the binding potential or stickiness of a psychedelic drug, whether it's LSD, mescaline, psilocybin, for a particular serotonin receptor, the serotonin 2A receptor, 2A, the more sticky, the more potent. So that relationship was discovered in the mid-1980s, discovered in animals, looking at head twitches, which is our kind of behavioral readout of a rodent that's tripping, that they sort of shake their head. We don't really know why, but that's our readout of whether the psychedelic's working or not in animals. In humans, you can just ask them about the effects. And there you can see that the dose required for people to feel the effects correlates extremely strongly with the drug's particular affinity for the serotonin 2A receptor. And that near perfect relationship between affinity or stickiness for the 2A receptor and potency doesn't exist for any other serotonin receptors or any other receptors in the brain. So it's that level of specificity that I think is quite remarkable, actually, and it's amazing, actually, that it's not sort of common knowledge for anyone who's interested in psychedelics, that we know with such a high degree of specificity that, for example, if you block this receptor by giving a drug that binds to it but gets in the way of another chemical that might come in and signal at that receptor, just blocks, we call those antagonists, people don't trip. So you give the block that receptor, you give a big dose of LSD, you're not going to feel it, So really solid scientific evidence for the importance of the serotonin receptor, and really the importance of the brain to all the weird and wonderful things that can happen with a psychedelic. And so that's where we are with serotonin and the 2A receptor being really important. We also know now through some recent brain imaging work that you can look at the proportion of these 2A receptors, most of which are found in what we call the cortex, which means bark, actually, like the bark of a tree, the outer layer. And in humans, our brains are so weird because, first of all, they're massive compared to other animals, and especially compared to body weight. Actually, whales have bigger brains, but they have massive bodies. So in humans, we have massive brains, but our bodies are, so big, not as big as a whale. And what's weird about our brains is just the sheer amount of cortex that we have. And cortex is associated with higher level functioning, processing, computational processing, thinking, and in humans, kind of this associative, analytical thinking. We have a lot of what we call association cortex that you don't have in other animals. They have the sensory cortex that does, the hearing and, seeing and smelling. But humans have a lot of this sort of extra cortex that we think is related to our associative, analytical style of thinking that's pretty unique in our species. And so these 2A receptors are disproportionately expressed in cortex that humans have so much of, and disproportionately expressed in the high-level cortex associated with this high-level cognition or thinking. We know recently, through using a brain imaging technique called positron emission tomography, which I'll talk about later on, that you can look at the proportion of available 2A receptors in the brain and how much of those, what percentage of those is occupied by a psychedelic that you give. And this work's been done with psilocybin, which is a key psychedelic chemical found in so-called magic mushrooms. And we know that around, if you give a dose around 20 milligrams plus and you occupy about 60% plus of the available 2A receptors, you're going to get very strong effects. And just recently it's been found that there's another strong relationship. In this case, it's not entirely a straight line, not a linear correlation like with a 2A affinity and potency, but it's a non-linear quadratic relationship between the proportion of 2A receptors that are occupied by the drug, the psychedelic, and the intensity of the effects that you feel. You give a low dose, you occupy, 10, 20%, you're going to feel it a bit. You give a higher dose, 20 milligrams of psilocybin or more, you're occupying now 60, 70%, you'll feel it a lot. And it's not a perfect linear relationship, it's sort of an inflection point. There's a kind of step function. You give over a certain dose and the experience becomes qualitatively and quantitatively in terms of intensity, much more. You jump up in intensity and effects. And it's in that kind of 60% plus range, 20 milligrams plus, that you start to get the really interesting effects with these psychedelics, the kind of thing that... kind of things like ego dissolution and these spiritual type experiences that we'll talk about later on. So all of this is really solid evidence for the importance of the 2A receptor. So that's where it all begins. And it's very important, I think, when you can get whisked away by all the magic associated with psychedelics, visiting the spirit world and seeing DMT entities and all that, it grounds us and it says this, like we think everything, is a thing of nature, a thing of these dimensions in this universe, and we can pin it right down, to quite a low specific level, at the molecular level, this particular serotonin receptor you need to stimulate to go to the spirit world. It's one of those really grounding principles. And perhaps like a reminder of the value and power of science that we know this. And so a key question when you know this, really, the importance of this receptor is why is it there? Why do we have it at all? What does it do? If you're stuck on psychedelics, you might think, oh my goodness, maybe it's there for psychedelics. And that's an interesting thought, and people have entertained that thought. And there are some good reasons and bits of evidence to assume that we have chemicals swimming around in our bodies and even in our brains that can be psychedelic. We have DMT, dimethyltryptamine, very closely related to serotonin, looks a lot like serotonin, as do a lot of these psychedelics. There's a hint there about how they're working. They're kind of hijacking the natural neurotransmitter itself, serotonin. They look like it. They're kind of serotonin imposters, and they come in, they kind of hijack that natural system, and they do their thing. But we have DMT, dimethyltryptamine. Serotonin is 5-hydroxytryptamine. So very closely related. You look at the molecules, they look almost identical. And we have a little bit, a very low concentration of DMT swimming around in our bodies and our brains anyway. We don't really know why. Maybe it's just a breakdown product of chemicals that are more ordinarily involved in signaling and such like in the body and the brain. And it's thought that the levels of DMT that are in the body and in the brain are probably too small to be functionally important. But even so, just to say that idea has been entertained, and people like Rick Strassman have put forward the idea, an American psychiatrist, written a very impactful book, DMT, the Spirit Molecule, put forward the idea that DMT might be released during extreme states like dying. And actually now there's some evidence that that concentrations of DMT do indeed leap up when you induce a heart attack in a rodent, for example. The problem there is that a lot of chemicals leap up because the animal's dying and its cells start to break down and they spill their content. So serotonin, its concentration leaps right up. I don't know what it is, something like 400 times its ordinary concentration is found in the brain during these conditions when the animal's dying. But that aside, that possibility that should never be ruled out, you should never really rule anything out. Let's address that question again. Why are these serotonin 2A receptors there? What do they do? They could be there for a naturally occurring psychedelic like DMT, or maybe they're there for serotonin. And there's this rule in sort of rational thinking, Occam's razor, that you should tend to go with the simplest, most plausible explanation, picking from a range of different possibilities. Yeah, maybe not the one that makes your spine tingle with excitement, that we have a naturally occurring psychedelic that's there, and that's why we have these 2A receptors. But perhaps it's there for serotonin, That's probably the most simple and plausible reason for these receptors being there. And so then, what does it do? What does it do? And we know that the most reliable way to release serotonin, and this might sound a little counterintuitive at first when you think of serotonin as a sort of happy hormone, the most reliable way to release serotonin is to stress an animal or cause some kind of pain. But if you think about it a bit more, maybe it does make sense, because the most reliable way to release endorphins, naturally occurring pain relievers, is to cause pain. And so maybe there's a clue there that you release the serotonin and it's going to counteract, it's going to address, it's going to be a response to stress. Maybe that's its function. And this is a useful way, I think, of thinking about a bit of a mystery, really, in psychopharmacology, drugs in the mind, in the brain, mystery in science, what's serotonin for. But a strong candidate is that it's there, in the brain at least, for some kind of response to stress. And adaptive responses to stress might take a few different forms, and maybe there are different serotonin receptors that address those different responses to stress. But because we're interested in psychedelics and we're interested in the 2A receptor, what might its signaling do that's functionally useful as a response to stress? And to answer that, we can look at a lot of evidence that we have. First of all, that stress paradigms, a number of different kind of varieties of ways in which you can stress an animal. Quite sad in some ways, of course, that this research is done, but it's done. We have this information. Stressing animals, you don't just release serotonin, but you increase the availability and also the functioning, generally speaking, of the 2A receptor. It's quite a specific and very reliable relationship. Stress an animal, the more intense the stress and the more chronic or long-lasting the stress, the bigger the effect. And what happens is, it's a term we refer to as upregulation. It just means an increase, really. We upregulate the functioning of the 2A receptor. So another kind of clue that this receptor is involved in a response to stress. So to focus in now about the specific response, you can look at different evidences that show that stimulating the 2A receptor, the serotonin 2A receptor, increases plasticity in the brain. And we can have a number of different markers of plasticity. You boil that term right down. What does it mean? Really, it's about the ability to change. And plasticity can mean that you you change your behavior, or maybe you're just supple and you reinforce your behavior. So it's not always like the breaking of patterns of behavior or thought. It can be the stamping in of patterns or thought. It just means that you've got a supple mind and brain or system that you can, that's pliable, that's malleable, that you can move in a particular direction. And that's what 2A receptors seem to do. They seem to be strongly associated with plasticity, the potential for change. And so that's another clue about why they're there. There's also strong evidence that the 2A receptor is involved in learning. Learning and plasticity go hand in hand. Another component of learning is what we call extinction learning or unlearning. So you've stamped in some kind of behavior, like an addiction, for example. What can you do to sort of rewrite that learning? Well, you can induce plasticity, the ability to change, and then you can try and break associations, you know. So that's extinction learning. And if you can enhance that, maybe you can treat addiction, for example. And so if you're inducing plasticity through the 2A receptor, you have a system that is very sensitive, and it's sensitive to the conditions that it's in. If you provide conditions that are going to stamp in a certain kind of behavior, you're going to stamp it in more easily because you have that supple plastic system. But if you provide conditions that are going to shift you in a particular direction, guide you in a particular direction, then that's going to be enhanced. So there's a really important rule here that's starting to emerge in relation to serotonin itself, but particularly this serotonin 2A receptor that is hijacked by psychedelics. And the rule is that serotonin, and the serotonin 2A receptor specifically, is strongly associated with our sensitivity to context, sensitivity to the conditions that we're in at any given moment. And a lot of different things you can bring in here, like strong evidence that the 2A receptor is involved in brain development. As we mature, it's involved in modulating and mediating how the brain matures and develops. Levels are very high early on in life and drop as we hit sort of middle age, whether that's associated with a kind of sort of ossification or, you know, rigidity of thinking and behaving as you enter that part of life is an interesting question, maybe. So that's where we are. Serotonin, that's what psychedelics are working on. They're working on that aspect of the serotonin system that is associated with plasticity, and they're inducing a state where we're very sensitive to our conditions. And those conditions might be right there and then in the environment, but there's another environment to think about, and that's the inner environment. It's what's in your head to begin with. And if these compounds are, psychedelics are sort of flattening the sort of hierarchical nature of the brain. So much of nature is organized hierarchically, and there are different things that sort of enslave things, you know, a level down. That kind of mastery-slave relationship is found throughout nature, and it's very much found in the brain. Likely explains a lot of how the brain works. But through this 2A receptor, there's good evidence that you're relaxing that kind of enslavement, and so in that kind of open playing field, you have this supple system that's going to be sensitive to what's out there, but it's also going to allow for what's in there to be more easily accessible. And all of this might intuitively bring you to that theme that was emphasized initially actually by Timothy Leary, who we'll talk about in the next section, of set and setting. Set is your mindset. It's that inner environment. It's what you bring to the experience. You know, in psychoanalytic terms, you might think of it as the unconscious mind, or Aldous Huxley referred to it as the mind at large, the mind sort of beyond ordinary sort of conscious access. That's the set. It includes more superficial things like your expectations, but maybe it also includes things like, what happened in your childhood, or maybe even further back, what happened in you as a human being, in terms of your ancestry, the collective unconscious, as Carl Jung would refer to it. So all of that can become more available and accessible. That's your set. And then the setting is simply what's there in the environment, people that you're with, the music that's playing, maybe the stress that's in the environment. And so, let's come back again. Serotonin 2A receptor, plasticity, sensitivity to context. That's likely what this receptor's there for, and good evidence that if people, whatever you're being, whether you're a rodent being stressed in someone's laboratory, or you're a human being encountering the ordinary stresses of life, but perhaps they get really intense and you've got some existential threats to your very existence or sanity, what's going to be happening in your brain is that your 2A receptor is increasing in availability and functioning. You're getting very plastic, very sensitive, and context sensitive, and you could sadly enter a psychosis and go in that direction. You hit a fork in the road and you can move off to madness, or you can have some kind of existential revelation and transformation, and maybe you find God and you start to take up spiritual or religious practice. You have a conversion experience, or so it's a fork in the road, and these are supple plastic states. I like to call them pivotal mental states, because they could either move towards pathology or they can move towards, I think they call it apathology, but wellness. So it's an opportunity, and we'll talk about this later on, how you can harness that opportunity therapeutically, to try and treat mental illness, or just generally move someone towards a state of enhanced psychological wellness. So just to rehearse what we covered there, we talked about what psychedelics are, mind revealing. We talked about how they work at the molecular level, that we know that, and we know it quite precisely, that they work on the serotonin system, very complex neuromodulatory system in our brains. They work on a particular receptor subtype, the 2A receptor, serotonin 2A receptor, found in high concentrations in the cortex, that aspect of brain that humans have so much of, and especially so in the highest level aspect of cortex, in the association cortex. That's where you see these key kind of gateways that psychedelic work through, molecular kind of gateways, the serotonin 2A receptor, where it all begins. They're there in high concentrations, in hierarchically the highest aspect of brain that, to our knowledge, we know even exists anywhere in the universe so far. By stimulating these receptors, we induce a state of plasticity, ability to change. And so in a state of high sensitivity, you have a system that is shapeable, that can be guided in a particular direction. And if that state arises naturally through stress, for example, adversity, then sadly you might move towards illness, and maybe something like a psychosis in an extreme case. But perhaps you induce that state, so for example with a psychedelic drug, or maybe even some kind of ascetic practice that creates a kind of stress to the system, but you've intended for that stressing of the system, and you utilize the subsequent plasticity to move you towards wellness. So that's where we are In the next section, we're just going to rewind a little bit and cover the history of the science of psychedelics. So maybe a little lighter and hopefully interesting. Thank you.